Have you ever wondered how rockets get to Mars? Well, they use something called a Hoffman transfer. Now, it sounds a little confusing, but I'll break it down for you, don't worry. Okay, but what does any of this mean? Well, this is what a Hoffman transfer looks like, kind of. I hand drew this diagram to help it, make it easier for you guys to understand. This green line, this green circle, that's Earth's orbit. This red line, Mars's orbit. Line, it's a circle. Duh. Mars and Earth both orbit the sun in circles, or technically ellipses, but they might as well be circles. There's a guy named Hoffman, and he found out that the most energy efficient to get your rocket from one planet to another was using this elliptical orbit called the Hoffman transfer orbit. So how do we actually use a Hoffman transfer orbit? Well, first we have to wait for the Earth and Mars to get to the right spots in their orbit. The angle is about 44 degrees, where Mars is ahead of Earth in orbit. They're both orbiting counterclockwise. It's different for every planet, but, we're talking about Mars here. Now, once the planets are aligned, then we launch a rocket from Earth, get it into orbit, and then once that rocket is in orbit, we're going to be firing our thrusters at the right spot, at the right direction, and elongate the orbit until it looks like this. See, an orbit around Earth, goodbye, would look a little something like that. And that little arrow is going to be our rocket. Now, if our rocket starts using its thrusters, it can expand its orbit till there, then till there, till there, and eventually to our orbit that we want. Okay, so we have our rocket, and it's heading in this orbit to Mars. So when our rocket is moving through this orbit, Mars is also moving at the same time. When our rocket's here, Mars is probably there. When our rocket's here, Mars is probably there. And by the time these orbits intersect here, Mars is going to be here. We know this for a fact. That is the whole point of this transfer orbit, to get the most efficient and speedy way of getting to Mars by using the least fuel. And it just so happens that they intersect there because of math. So we have our rocket. Now, it's here, but it's moving that direction, and it's moving like a lot in that direction. The actual orbit is that big. So how is it going to stop? Well, what we're going to do is right here, when it's closest to Mars, that's when we're going to turn on our thrusters in the opposite direction we're facing. Our rocket turns around, does a 180, and starts pointing in that direction and shooting its thrusters back in the direction that it's going. It's moving in this direction, but its thrust is moving in this direction. It's accelerating in this direction, but it's moving in that direction. Its orbit is going to start out huge, the size of a solar system, but as it's accelerating in the opposite direction as it's moving, it's going to slow down and make its orbit smaller. This is its orbit, and it's doing this maneuver, slowing down, and this is what its orbit looks like. But then its orbit gets a little smaller. It gets a little smaller, and then it gets a little smaller again, and again, and again, and again, and eventually our rocket's going to have a pretty circular orbit. I hope my little demonstration was good enough, but eventually, after enough of this acceleration backwards, our rocket is going to have a relatively circular orbit, and it'll eventually be able to land down on the surface and meet his alien friends, and everyone's happy. I hope you enjoyed my little whiteboard demonstration of how a Hoffman transfer actually works. If you want to see more, definitely subscribe if you're watching this on YouTube, or follow if you're watching this on Twitter. Like the video, all of the above. Thanks for watching.